Hello everyone, and welcome back to our physics and mathematics problem-solving session. Today, we're tackling a fundamental concept in thermodynamics, the work done by a gas. Specifically, we're looking at a scenario where 1 mole of an ideal monatomic gas is heated at constant volume from 300 Kelvin to 600 Kelvin. Our goal is to find the work done by the gas. Understanding this concept is crucial for grasping energy transfer in thermodynamic systems, from engines to atmospheric processes. First, let's visualize this problem. Imagine a simple diagram showing a gas contained within a sealed, rigid container. Think of a cylinder with a fixed, immovable piston. This visual helps us confirm that the volume of the gas cannot change. Next, let's identify our key variables and constants. N. This is the number of moles of the gas, indicating the quantity of gas. For this problem, N equals 1 mole. T1, our initial temperature of the gas, which is 300 Kelvin. T2, our final temperature, 600 Kelvin. The critical condition here is constant volume. This means the volume of the gas, V, does not change throughout the heating process. Now, let's recall the relevant equations and principles. The work done by a gas, denoted as W when it expands or compresses, is fundamentally defined by the integral of pressure with respect to the change in volume. We express this as W equals integral P dV, where P is the pressure of the gas and dV represents an infinitesimal change in volume. This equation directly links the work done to changes in the gas's volume. With our equation in hand, let's substitute our known conditions and solve. The problem explicitly states that the gas is heated at constant volume. What does constant volume mean for dV? It means there is no change in volume whatsoever. Therefore, dV is precisely 0 at every instant during this process. If dV is 0, then when we integrate P dV from our initial to final state, the entire integral evaluates to 0. So the work done by the gas, W, is 0 joules. Let's check this answer for consistency. Work in physics is done when a force acts over a distance. For a gas, this typically involves the gas expanding and pushing against its surroundings, moving a boundary like a piston. If the volume of the gas remains constant, it's not expanding or compressing, its boundaries aren't moving. Therefore, the gas is not performing any volume work on its surroundings, nor are the surroundings doing work on the gas. A result of 0 work done is perfectly consistent with the definition of work in thermodynamics for a constant volume process. In conclusion, for 1 mole of an ideal monatomic gas heated at constant volume from 300 Kelvin to 600 Kelvin, the work done by the gas is 0. This highlights a crucial principle in thermodynamics. For any process occurring at constant volume, what we call an isochoric process, the work done by or on the system due to volume change is always 0. This principle is widely applicable, for instance, in understanding internal combustion engines during certain phases, or simply when heating a sealed container of gas. It's important to distinguish this from heat transfer. While no work is done, heat is transferred to the gas to raise its temperature. The first law of thermodynamics, which states delta U equals Q minus W, tells us that for this constant volume process, where W equals 0, the change in the internal energy of the gas, delta U, is entirely due to the heat added, Q. The key takeaway from this problem is simple yet profound. No volume change means no work done by the gas. This fundamental relationship between work, pressure, and volume is a cornerstone of thermodynamics. It demonstrates how specific process conditions can dramatically simplify our calculations and provide clear insights into energy transformations within a system. This concept is universally applicable to any gas or fluid undergoing a constant volume process, serving as a building block for understanding more complex thermodynamic cycles and energy systems. Thank you for joining me in this session. If you found this explanation helpful, please consider liking this video, sharing it with your friends, and subscribing to the channel for more physics and mathematics content. Feel free to leave your questions or comments below. And if you have a specific physics or mathematics problem you'd like to see solved in a future video, you can support the channel through a donation. Each month, we'll select a few problems submitted by our generous donors and create dedicated videos to help you understand them better.